third year student. This is Devang Shah from LG Institute of Engineering and Technology. We have been learning the subject basic electrical engineering. So in our previous session we have discussed about series RLC AC circuit, where we observe the behavior of resistance, inductor and capacitor once they are connected in series and under the excitation of AC signal. We have to observe one more parameter which we define as a frequency. Now you can see here, as a part of our AC circuits, if we again continue, I am going to connect my circuit like this way. Here for one branch I am going to take resistance and inductor in series, but this combination is in parallel with the capacitor C. This becomes a parallel RLC AC circuit under the same AC applied voltage, which is called Vt is equal to Vm sin omega t. So here you can see from this circuit diagram, Vt is equal to Vm sin omega t, where we have applied to this parallel combination of RLC circuit, right? So from this, if you check the phasor diagram, where you will find the x component is a cos component and y component is a sine component. From here, the parallel RLC circuit, you can always find the current magnification, not the voltage magnification, right? So here, as such, it's a parallel combination, so values of current are different, but the voltage drop across each branch is same. So here my job is to find the current component for this phasor diagram. So you can see here, x-axis you will find the current I, that is equal to IL cos omega t, and you can see on a y-axis you will find IL sin omega t. One current which is passing through resistance and inductor. This series combination, you can see here the angle phi L, effective current of this particular branch where you have connected resistance and inductor together, for this particular branch is current IL, and the current passing through capacitor is IC. So here from this series combination you will get total two currents, one current which is passing through resistance and inductor and another current which is passing through capacitor. So the current which is passing through resistance and inductor I define as IL, this is a one current component, and the current is passing through capacitor, this is called IC, this is another current component, right? So if I want to plot these two currents on a phasor diagram, you can see here, since R and L both are in a series, so here current is lagging by angle phi with respect to voltage, right? So you can see for only R and L, you will find the current component IL, x component of current you can define as IL into cos omega t, right? And for a y-axis you can see here IL sin omega t, right? But this is for only one branch. Let's say another current IC which is passing through capacitor, since there is no resistance is connected here, so current is leading by angle 90 with respect to applied voltage V. So you can see here for a positively y-axis you will find the current IC. So here let's try to expand these two current components IL and IC by this way. So here at the resonance frequency, to find the resonance frequency, we make use of this equation where IC is equal to IL sin phi. You can see here from y-axis the positive term is IC and the negative term is IL sin omega t. So I'm going to equate this two current and I'm taking IC is equal to IN sin omega t. So from this phasor diagram, if you apply the trigonometry, then IC is equal to IL sin phi, where IC is equal to V divided by XC, and IL is equal to V divided by ZL, where ZL is equal to under root R square plus XL square, right? So you can put the sin phi is equal to XL divided by ZL. So from this you can find the ZL square is equal to XL into XC, right? So further you take the term XL is equal to 2 pi FL and XC is equal to 1 by 2 pi FC. From this you can find the ZL square is equal to L by C, right? Again you further take ZL square is equal to R square plus XL square. So that is R square plus omega R square into L square is equal to L by C, and you convert the complete equation in terms of the resonant frequency. You can see here the resonant frequency for parallel RLC circuit FR is equal to 1 by 2 pi under root 1 by LC minus R square divided by L square, where the value of R square divided by S square is very negligible, hence you can neglect it. It's very small, so you can neglect it. So here the effective value of resonant frequency Fr, that is equal to 1 by 2 pi under root L and C. Now the equation is same for series RLC AC circuit and parallel RLC AC circuit. So further, if you discuss about the impedance factor of this parallel RLC circuit at resonance, you can see here I is equal to IL cos phi, where you put the values of I is equal to V by Z, IL is equal to V by ZL, and cos phi is equal to R by ZL. That is from the phasor diagram, from the trigonometry. So from this you can be able to find the effective impedance Z is equal to ZL square divided by R, where ZL square, that is equal to L by C from our previous slide. So you will find the total impedance of this parallel RLC circuit Z is equal to L divided by RC. That means here the value of impedance depends on the values of inductor divided by the multiplication of values of R and C. So here you can find I is equal to V by Z, and that will be the minimum. So here current value is minimum because at the resonance value of Z is maximum. The value of impedance is maximum. So you can go through one by one all this equation, and I is equal to V by Z, and that will be minimum. Now again for this, if you find the quality factor of this series RLC circuit, then quality factor is nothing but the current magnification. So for a series RLC circuit, that was a voltage magnification. Now in a parallel RLC circuit, that is a current magnification, where you can take as a IC divided by I, and if you put the values of IC and I, like IL sin phi divided by IL cos phi, so from this you can find the tan phi, and tan phi is nothing but omega R into L divided by R from the trigonometry from this triangle. So if you put the value of omega R, that is equal to 2 pi Fr into L divided by R, and here you put the value of Fr is equal to 1 by 2 pi under root L and C, you will find the Q factor as 1 by R into under root L by C. Now the equation is same for series RLC circuit or a parallel RLC circuit, but for a series it is a voltage magnification, and for a parallel is a current magnification. Right now again we can define the graphical representation of this parallel RLC circuit, where all these different parameter we are going to consider with respect to variation in a frequency. So here x-axis you can see I have taken as a frequency. The frequency starts from 0 up to certain kilohertz, megahertz and gigahertz, and with this respect, if I am going to correlate all these parameters with changes in a frequency. Right now this case I am taking all parameters same as a part of the series RLC circuit, but I am taking the reciprocal of all parameters in parallel RLC circuit. So first term is called the conductance. Conductance is nothing but the reciprocal of resistance, right? So resistance for the series RLC circuit, but conductance is here for the parallel RLC circuit. So it is again the independent of frequency. Again it's a straight line. So here there is no relation of the frequency. Even you are going to change the frequency from 0 to certain kilohertz, there is no change in a conductance. So conductance remains constant for any change of frequency. Here again the inductive susceptance. Now susceptance is nothing but the reciprocal of reactance, right? So you can find here it is inversely proportional to the frequency, as BL is equal to 1 by J into XL. So from this you can be able to find 1 divided by J into 2 pi FL. So from this you can say the inductive susceptance BL is inversely proportional to frequency. That is the again that's shape is like the parabolic. Here you can see where the at a low frequency you will find the value of XL is higher, and at a high frequency XL decreases. Same way you can find the capacitive susceptance is BC, and you apply this equation, BC is equal to 1 divided by minus J into XC. So here BC is proportional to the frequency, right? So this relation we define as a linear relation. If frequency increases, BC increases. If frequency decreases, BC decreases. You can see here as a straight line, that's a linear relation, right? Now from this you can find the admittance. Now admittance Y is nothing but the reciprocal of impedance. So I can define here Y is equal to under root G square plus BL minus BC square, right? So at the resonance, BL is equal to BC. So you can write here Y is equal to Z here. So Y is equal to Z. So admittance is same as the conductance at the resonant frequency. So throughout this frequency axis, I have to find one point as my resonant frequency FR, and that I define as the green dotted line. You can see the green dotted line where it intersects the frequency axis, that defined as a resonant frequency, and at resonant frequency your admittance is equal to conductance G, right? So you can see here that is that intersect this line, right? Hence this is a XC and XL. So at one portion where at I mean um, from 0 to resonant frequency line, you can see the value of BL is greater than BC. So that part is more inductive, while from FR to higher frequency, you can see where the value of BC is higher. So that part is more capacitive, right? So as such, you can see the curve of admittance, and exactly the here the value of current I is equal to V into Y, right? So the so here the current is also minimum as the admittance is maximum at the resonant frequency. So here if you see this equation, I is equal to V into Y, so here current is also proportional to the impedance Y. So within a same shape you can find the current, right? Now about the power factor. So this power factor cos phi is equal to G by Y, which is inversely proportional to the admittance. So at the resonant frequency, the value of power factor cos phi is unity. So you can see it is exactly a reverse slope of the admittance Y, right? So this is all the graphical representation of parallel circuit. Hence the shape of series RLC circuit and the shape of parallel RLC circuit both are same, but here in parallel case we have taken all the parameters in a reciprocal, that is what we have taken in series RLC circuit, right? So dear students, here you can also go into detailing and find the differences of the graphical representation of series RLC circuit and series RLC circuit and parallel RLC circuit at resonance condition, right? Um, Thank you very much, dear students. If you have any query, you can write in my comment box. Thank you very much.